So pretty much all of this course, we're going to be using what's called Fidesa, the six-step problem-solving method. I'm going to walk you through what that method is with a practice problem. So the F for Fidesa stands for find. You can kind of think of this as a simplification or restatement of what the problem is actually looking for. So our example problem here is a 5-kilogram ball is initially at rest. It undergoes a constant acceleration of 2 meters per second squared. How far has it gone when 10 seconds have passed? So the thing we are looking for is how far the ball goes. And I don't just want to restate, okay, how far does the ball go? I want to think in terms of the equations and the formulas I'm going to be using. The distance in terms of how far a ball will travel is either delta x or delta y. In this case, I can kind of pick the most standard one we use is delta x. So I would write delta x here as the variable, the thing that I'm looking for. So it helps me spot the equation I know I'm going to need later. So that is kind of the simplification for F, the first letter in Fidesa. Again, that is find what is it I'm looking for. I for image, this is simply a redrawing of the problem. This can be just a picture of what's going on so you can kind of get a visual of it, or a free body diagram, which we'll talk about later. In this case, if it's a ball that's initially at rest and is undergoing constant acceleration, once it's accelerating, I know it starts moving. So I can just draw the ball with an arrow pointing, showing that it's moving. And I can deduce from this by drawing it, this is only going to be one-dimensional. It's going to move in one direction. I know that because acceleration is a vector. If it's just one acceleration, it's just going to go in one direction. The next, so I image, that is the second letter for our acronym in Fidesa. D, the third letter in our acronym for Fidesa, is called data. And this is restatement of all the numbers or values I'm explicitly given, as well as the ones I'm implicitly given. So I'll explain that in a second here. The explicit numbers, I see 5 kilograms, I see 2 meters per second squared, and I see 10 seconds. 5 kilograms is the mass of the ball. We represent that with the letter M. So, and again, like in the find, I'm going to attach the variable that I would see in a function or formula. I'm going to do the same thing here. So the M would be 5 kilograms. A is the letter we use for acceleration. That would be 2 meters per second squared. And then T's time, that would be 10 seconds. These are all the ones I'm explicitly given, meaning they're just plain stated in the numbers. I have one more value I'm implicitly given. It doesn't outright have it as a number, but because it tells me the ball is initially at rest, that tells me the initial velocity. We would represent that with a V, little naught down here. That's not technically a zero. It's not, kind of means essentially initial velocity of the system. I would say that that's 0 meters per second squared. So again, that's D, my third letter in the acronym. D stands for data. E, my fourth letter in the acronym, stands for equations. And this would be any and all equations I either know I need or think I might need to solve this problem. And the way we determine what equations those would be is I'm going to match all the letters I'm given and the letter I'm looking for. And sometimes this can be I need a combination of equations. For this particular problem, it actually fits one equation rather perfectly. It's one kinematic equation that you'd have like in a list for a formula sheet, but the kinematic equation is delta x equals v initial t plus 1/2 a t squared. And that would be like on a formula sheet that you would have. So and it turns out that's really the only equation I need. It's already set to solve for the thing I'm looking for, and I have all the other parts to it. So that brings me to the next letter in my acronym, S. And this stands for solution set. Solution set would be any rearranging of the equations or adding the equations that I would need. So in terms for this case, there's actually really not much I need to do here. It's already set to solve for delta x, which is how far the ball goes. That's equal to v naught t plus 1/2 a t squared. And I know all these values. They're given to me here. But in some future problems that we will look at, either we need to combine two equations or we need to rearrange them to solve for another variable. So, but in this case, it's actually already solved for the variable I need, and I didn't need any other equations. So we're set and we're actually done with this part here. The last step, A, answer, is where I plug in all my numbers into this equation. And when I plug in all my numbers, I will also include all their units, which can seem kind of tedious, but the inclusion of the units is really important because, so I want us to think, if I'm looking for how far a ball goes, I'm looking for a distance unit. In our general default distance unit that we're given in physics is meters. But sometimes I have to pay attention if I'm given velocity in meters per second, but maybe I want to find inches. There might be a conversion I need there. So you will always want to include your units because your units will cancel out in the algebra. When I do the equation, if I input all my units and I look at the equation, I do the algebra properly, the only unit I will have left is meters because that's what I'm looking for. So for the first case, I have an initial velocity of 0 meters per second. I have 10 seconds is the time it undergoes, plus this is 1/2. My acceleration is 2 meters per second squared, and then this is going to be 10 seconds squared. So you'll notice anything times 0 is just 0, but the units for this would cancel out. I'd be left with meters. And the important thing for, you can think of it kind of like with fractions. I can only add fractions that have the same denominator. The same is true for units. Like I can't add a volume to a distance unit. I can only add a distance to a distance unit, right? So I can add meters to meters. I can add liters to liters. I can't add a meter to a liter is the kind of example I'm going for that. But anything times 0 is just 0, so that all goes away to 0. This is, you can think, now this is order of operations. It's everything is multiplied, so except for this needs to be squared first. So, but I can take the 1/2 and the 2, that just goes to 1. You'll notice, so I have 10 seconds squared. The seconds is also squared, which is why it cancels out with the second squared in the denominator for acceleration. So that unit also cancels. You'll see I'm also left with meters again, which is good. That's how I know my units check out. That's how you know you've done the problem correctly. If I end with the unit I'm looking for. 10 squared is 100 times 2 divided by 2. That's going to give me 100 meters. And that's the distance that this ball has traveled. You'll notice one other thing. I was given the mass, but did I actually need it? So I want you to pay attention for future problems that we'll look at. Occasionally that'll come up where you'll be given a variable and you'll find you don't actually end up needing to use it. This will happen. It can be tricky sometimes to pay attention to that. So just because they give me mass doesn't mean that I had to find an equation that had to have mass in it, okay? And that would be how we will apply the 6-step Fidesa problem-solving method.